Hi, my name is Ted Lawrence and I'm a professional chemistry and physics demonstrator. I tour the Northeast doing science shows for elementary schools. Got quite a reputation in my alter ego as Dr. Quentin Quark. You might want to see me demonstrate simple machines by leaping over Shaquille O'Neal's head. I don't have time to set that up today. You might be interested in watching me have 1,000 kids explain how each of Newton's laws are demonstrated if I discharge a fire extinguisher while I'm wearing rollerblades. But if you want to see that, come check out the CPTV Science Expo at the end of April in Hartford. Maybe you'd like to see me demonstrate rotational dynamics by doing a loop-de-loop with a bicycle. Unfortunately, that hasn't worked yet. The loop isn't big enough and it might need to be a little more colloidal before it works, but I haven't given up yet. Of course, that entire demonstration would be easier to do were I to use a globe of death and a motorcycle, like the guys do it on Ringling. You get me one, I'll do it. Or to teach about projectile motion, or even more rotational dynamics with a wheel of death or human cannonball. I'd be game to do all of them. Unfortunately, I don't have the resources to do that today. I've got one day off this month. I'm going to try to shoot a quick video for you guys right here, right now. I have to apologize for the small scale of these demos. Normally, I like to do things big. I like to use really big production values to make my lessons stick really, really well. I've got a limited amount of time today. I thought of something this morning. I'm going to try to make it into a lesson for you right now. It's about gravity. You've seen a lot about gravity before, but you might want to watch all the way to the end. So I want to do a quick lesson about pendula, since we're talking about gravity. Pendula are an application of gravity. Because gravity is always constant, gravity makes pendula work, swings to and fro. And they're so consistent that we actually use pendula. We have for centuries used pendula for timekeeping devices. For instance, on a metronome, it's an inverted pendulum. The mass is at the top, but it's still a pendulum. For cuckoo clock or grandfather clock, how long or how short you make the pendulum determines how fast the clock runs. So it's very, very adjustable. You can make it run exactly as fast or as slow as you want. It just takes a little bit of time. Because pendula are run by gravity, their amplitude is constant. Unless you put more energy into them by giving them a shove, or unless you put more energy into them by holding them up higher before you let them go, the amount of energy, because it's controlled by gravity, is constant. Or is it? Now, for some reason, there's a spring in clocks. For some reason, there's a spring in cuckoo clocks and grandfather clocks. But there's something that's kind of interesting about pendula. You see, friction is everywhere. What that means is that if I let the pendulum go, before it gets back to me, it's going to lose a little bit of its energy. It's not going to make it all the way back. Yeah, I agree. That's not really Dangerman style stuff. Let's go talk a little bit about kinetic and potential energy, as long as we're dealing with gravity today. Oops. Danger man. So at any rate, because gravity is constant, there's some other interesting things about gravity. We haven't discussed that science is a reproducible, predictable field. That's what separates science from other things. I've been in parts of the world where you could meet a guy who would hold something in his hand, and you ask him, what will happen if I turn my hand over and let go? Will it go down? And the guy would say, I don't know. The guy was not a scientist. A scientist is pretty sure that if he's in the vicinity of the planet Earth, turns his hand upside down and lets go, the Earth is going to draw that object toward it. Same way, every single time, because gravity is constant. So because gravity is constant, we also have things like potential energy and kinetic energy. Now, energy is what makes things dangerous. The definition for energy is that energy is what makes work happen, but I think of energy as what makes things dangerous. For instance, this sword is lying here on the stump. We know when it's just sitting here, it's not dangerous. Even if it's sharp, it's not dangerous, because it's just sitting there all by itself. In order for it to be dangerous, it would actually have to have energy. Now, if you pick up the sword and you start moving it, then it becomes dangerous. When it moves, it has something called kinetic energy. That's what makes it dangerous. Kinetic energy. But I can actually give you another example of when the sword is dangerous when it's not moving. If I draw the sword up to the ceiling, now Is it dangerous? I claim that it is. How dangerous? That's harder to know. But it's still predictable. Science is a wonderful thing. If you really understand science, if you really know what's going on, most importantly, if you know how to control all of the variables. Oh, Damocles. So, here's where we're at. I claim gravity is constant. Claim we can't control it, we can't manipulate it, we can't turn it off, we can't turn it on. It's gravity. We understand it, we can predict it, we can't control it. Up there, got the knife. It's got a dangerous amount of potential energy, thanks to gravity, as it hangs up there. If I release the knife, what's going to happen? How predictable is it? How many variables are involved? Has the anchor that's hanging from shaken? Have things underneath it moved at all? What if a truck rolls by? Makes things vibrate a little bit? What if air blows through the studio? Makes things change a little bit? I don't know. There's a lot on the line. But what I know is science. And I know that gravity is constant. This is Ted Lawrence. I want to be Dangerman. Remember, with science, you can do anything. But be careful. When you're Dangerman, experimental errors may scar you.